All right, in this video, looking at problem 4, identify each of the following as measurements of length, area, volume, mass, density, time, or temperature. So looking at A, PS. S is the SI unit for time, seconds. P is a prefix. It means trillionth. So a trillionth is a ridiculously small fraction of whatever, in this case seconds. So there, if you got together 10 to the 12 picoseconds, that'd be the same thing as a second. So picoseconds is a measurement of time. B, mg. G is, well, first of all, mass, right? If we're looking at the base units, right? There's only 7 base units. Kilogram is the base unit for mass, which is a 1,000-gram block. Milli means a thousandth. So there are 1,000 milligrams for every 1 gram. So milligram is a measurement of mass, and there are 1,000 milligrams in a gram. Capital K stands for Kelvin, and we'll talk about that in a little bit. It's a measurement of temperature. D, little k, little m squared. All right, so in this situation, the prefix is kilo, so it's kilometer squared, kilometer squared. So we're talking about area. So length times width, kilometer times kilometer gives me kilometer squared, which is the derived unit for area. So derived units, right? We have 7 base units from which we derive all other units of measurement. E, micro stands for millionth, so this is a millionth of a meter, measurement of length. Nano stands for billionth, so there are 1 billion square meters in a square meter. So nanometer, well actually no, it's a derived unit, so it would be different, but nonetheless. Nano means billionth, so very small area. And all right, so degrees Celsius. 2 units we use for temperature commonly in chemistry. They're just starting in different positions, right? Water is so pervasive in our world that Celsius is based off of water. So the scale starts, right, at 0 degrees Celsius. This is the freezing point of water, and nice and symmetrically, the boiling point of water is 100 degrees Celsius. Nonetheless, what it means to freeze is that you've got the particles moving so slow that they get locked into a crystal. So this is what you're measuring with temperature, right? How fast the particles are moving. So slow the particles down below 0 degrees Celsius, minus 40, minus 50, minus 100, minus 200, minus 273. At that point, the particles aren't moving at all. All right, back up at 0 degrees Celsius, it was kind of a jiggle to the particles. You slow them down to the point where there is no more molecular motion. At that point, you're starting the Kelvin scale. Kelvin starts where there's no molecular motion, and then, so either you're moving in the Kelvin scale or you're not. So 0 Kelvin, no motion. 1 Kelvin, 2 Kelvin, 50 Kelvin, 150 Kelvin, 273 Kelvin. You're now back to the freezing point of water, and this is a measure of how much of a jiggle those particles have. If you ever wanted to convert from one to the other, you just take your Celsius temperature and add 273 as a way to convert to Kelvin. So Kelvin, Celsius, just starting, they're parallel scales starting at different positions. Grams per cubic centimeter, right? Derived unit. If I weigh something, get its mass. If I displace these particles to get their volume, and I divide the volume in milliliters into the grams, I get grams per cubic centimeter, or grams per milliliter, right? They mean the same thing. So looking at the derived unit, it tells you mathematically what you had to do to get it. Grams over cubic centimeters means you had to divide cubic centimeters into grams. As I said, cubic centimeter, right? It's a measurement of volume. Length times width times height. Centimeter times centimeter times centimeter gives you cubic centimeter, which is the same thing as a milliliter. So they mean the same thing. Cubic centimeter is the derived unit. Milliliter is, I don't know, it's like a common unit, but you consider it matching up with the SI system. So we use them interchangeably, milliliter, cubic centimeter. What is the length of a pencil in the following figure if the ruler reads in centimeters? How many significant figures are there in this measurement? Okay, so looking at the ruler, it's a little bit hard to read. It looks like that pencil is greater than 7 centimeters and halfway in between, so 7.5 centimeters. This is my estimation on the 0.5, right? My eye sees 7.5 centimeters. So we understand there's a certain degree of uncertainty with that 5. So the significant figures here are the 7, which is the certain digit, and the 0.5, which is the first uncertain digit. So that's what sig figs are, right? Reporting the degree of accuracy with which we're measuring. If I had a better tool, right? So here's my tool that I was given. I estimated it at 7.5 centimeters. If they gave me a better tool, well, then I could make a greater assessment as to how long that red line actually is, right? With my new tool, I can see that, it's actually, I can make an estimation that's a little bit greater than 0.5, right? I'm estimating that to be to the hundredths position, right? The 1. So 7.51 centimeters. So my uncertainty is out at the hundredths position. Again, somebody else could see it too. So it depends on the eye. We understand the 1 is uncertain. So given the other tool, I'm looking at the tool here, right? If I want to read in miles per hour, it looks like I'm just past 70, right? There's 60 in terms of miles per hour. So I don't know, it's past 70, right? There's the dot. So 70.2 miles per hour. And if I'm looking at kilometers, it's, all right, so 100 and then 120. So 110 is the black line in between. So there's 112.5. So 72 miles an hour. Oh, there it is. 72 miles an hour, not 7.2. It's 72 miles per hour with the miles per hour gauge. So 2 sig figs in that measurement. And what am I doing here? Oh, I guess you're right. It's not 12, right? It's in between. So you're halfway in between 110 and 120. So it's 115 kilometers per hour. So 2 sig figs in my estimation as to how fast we're going in miles per hour. 3 sig figs in my estimation as to how fast we're going into kilometers per hour. Classify each of the following as a pure substance or mixture. If a mixture, indicate whether it's homogeneous or heterogeneous. Rice pudding. Well, rice pudding, I can see the rice and I can see the pudding. So it's a mixture of pudding and rice, and it's heterogeneous. All right, it's not the same throughout. Anytime you can see pieces, it's heterogeneous. So put a little note. Solid with a solid is always mixed together, are always heterogeneous mixtures. Seawater. Whole bunch of things dissolved in seawater. Calcium chloride, sodium chloride, little bits of that in this. Let's forget the little bits of that in this. We're just looking strictly at the seawater. It's the same concentration throughout, so it's a homogeneous mixture. So sodium chloride is a compound, water is a compound. They're mixed evenly throughout. Magnesium, Mg, is an element, so it's a type of substance. Ice is water, again, a pure substance. Classify each of the following as a mixture. If it's a mixture, indicate whether it's homogeneous, heterogeneous. Oh, okay, so we just did this. Air. Air is a mixture of oxygen and nitrogen. It's evenly mixed throughout. Tomato juice, I don't know. I can see little bits of pulp in tomato juice, so I say heterogeneous. Iodine is a element, so it's a substance. Sand, depends what your definition is. If you're looking at the beach sand, it's little bits of different kinds of rocks, so heterogeneous mixture if you're looking at sand. Beach sand, I should say. Give the chemical symbol for the following elements as appropriate. All right, so we're getting into this in the next topic in more depth, but we had an introduction to the periodic table. So sulfur is an element. It has a symbol, right? We use capital letters to indicate the symbol for sulfur. If we run out of uppercase letters, we use lowercase letters. So capital A, capital U, that would be the symbol for gold. Notice it's not G, right? So some of these symbols come from different languages, some of them from Latin. So potassium is not P, it's K. So some of these you're just going to have to memorize. Chlorine's easy, capital C, little l. Copper's easy, capital C, little u. Uranium, nickel, now sodium, right? Again, it's not S, it's Na. So whatever the source was of the word, it's not in English. So it's capital N, lowercase a for sodium. Gonna have to get used to memorizing some of these symbols. After the label fell off a bottle containing a clear liquid believed to be benzene, a chemist measured the density of the liquid to verify its identity. If you have a 25 milliliter portion of this liquid and it has a mass of 21.95 grams, Chemistry Handbook lists the density of benzene as 0.8787 grams per milliliter. Calculate its density and see if it agrees with the tabulated value. So is this benzene? It's a way of identifying it by its density, right? Benzene has a density. So it doesn't matter whether you have a little bit of density or a whole spill of density. Divide the milliliters into the grams to get the density of this sample of benzene. So it looks like it pretty much matches up. So yeah, I'd say that's benzene you spilled on the table. B, in an experiment requires 15 grams of cyclohexane, whose density is, what is it? And an experiment requires 15 grams of cyclohexane, whose density is, I'm missing the second part of this. It must be convert to milliliters, right? It's because it looks like I'm going to use the grams of cyclohexane as a starting amount, and I'm using the density to get to milliliters. I'm assuming that's what the problem here is. So the point is I can use density as a conversion unit to go from grams to milliliters. Second part of this question must have gotten cut off. That's what they want. Being able to use density as a conversion unit to go from grams to milliliters and milliliters to grams. So put what you want to get rid of in the denominator, the unit you want to get to up in the numerator in this case.